Here's a stack of 80 sheets of Bristol board, which I drew the schematics up to my machine, and then I went and took them to a store and got some pictures made up of it. They didn't do a very good job printing them. Dollar signs lit up in his head when he heard that I had 5 prints to print that I wanted to line up and make all the lines join up together. So he tweaked each and every print, made them a little bigger, smaller, and he noticed a lot of shade on the top part of it. And I wasn't going back spending another $150 and do it all over again, so I just made this my working drawing. It's I'll try to get up and slowly take a picture of it from one end to the other of the schematics. It's just 1/2 of the length of the machine. So that's all I need to draw up to explain how the law of physics works throughout it. So I'm going to take a walk down along the length of it best I can around the machine I got set up in my living room here, which I'll be showing you here shortly. And yeah, that photographer at that store running that photography equipment, and I should be money back if he doesn't do a good job, but unfortunately it wasn't. But that one up there I took a couple years ago on the machine. That's not too bad. That turned out all right because it's just a single print. And my machine itself is right here. I'll take some pictures of it all the way around. I get it all set up for my test to do the force test. And I'll demonstrate that here shortly. This is the middle of a winter day. I'm just using the sunlight to light all this up. So as you can see, it's quite a large machine. Now before they do the test here, I got a digital scale. It's going to show that's 1-to-1 ratio of a 20-pound weight hanging on it. And the schematics I used to have on this wall here, I set my camera up for about 3 months with a tripod and a kettleweight, make it stationary and never move it. And that's how I went and took a picture of each one of these segments, which I was hoping I can get a picture of, make it shorter and smaller where I can get one picture of it. So over here, I just recently wrote up an explanation how to start it from a standstill. I'll come over here behind my machine and see if I can read that to you. This is how to start from a standstill. 2 things are needed: a 12-volt battery and a compressed air tank. The 12-volt battery will power the solenoids throughout the machine, while the compressed air tank will power the pneumatic cylinders throughout the machine. The first thing to do is install a 12-volt battery. Next, to use the foot pump to pump up the air tank to 100 pounds pressure. Once that is done, push the start button. A regulator solenoid valve will close the air line to the foot pump, redirecting the compressed air to the potential energy input chamber. Okay, then you set the air pressure to the desired amount of power desired. Start out small and work your way up. For example purposes, we're going to use 12 pounds of force. This is sent to the potential energy input chamber, where it inflates an air bladder, producing an outward force in all directions. We're going to focus those forces into 2 opposite forces, pushing each other apart equally. From there, The two equal forces are going to be sent around an enclosed circuit to meet each other on a head-on collision at the other end of the enclosed circuit. One half of the enclosed circuit is a solid cable. The other half is a mechanical assembly. When the force from the mechanical assembly meets the force from the cable assembly, two different forces will meet each other on a head-on collision at a 1-to-1 ratio. Okay. The force from the mechanical assembly will be a lot greater than the force from the cable assembly. Now the law of physics will kick in. The greater force will cancel out the lesser force and motion will begin in the direction of the greater force. This motion will be used to pull the cable side of the potential energy input chamber along behind the mechanical section itself, thereby changing potential energy into kinetic energy without the loss of potential energy. The 12-pound force from the cable side will be stepped up to 3-to-1, making it 36 pounds of force when it reaches the meeting point to meet the force from the mechanical piston side, which will equal 60 pounds of force at a 1-to-1 ratio. Excuse me. That makes it quite a difference in the two forces meeting each other head-on at a 1-to-1 ratio. The left-over force can be used to do other things with, for example, turn an alternator producing clean, free electricity. The rest is history. Signed by myself, David Russell, on December 8th, 2021. Okay. We'll go back and we'll do a force demonstration at a 1-to-1 ratio of how much force it'll take to lift a 20-pound weight. And turn the scale on here. Hopefully you should be able to see it in the sunlight. And I'll try to hold this down. So it takes a little less than 7.5 pounds of force. I'll do it a few times. Yeah. And you can see the arrows there when they start moving. That's 1-to-1 ratio. So this demonstration is as far as I can show. And showing the demonstration how the law of physics works. Yet I can't get nobody to look at it. I mean, that's strange. Like the University of Alberta won't take a look at it. The government of Canada so far have been trying. They won't take a look at it and analyze it. So I don't know what else to say. So right now I've decided, well, I'll just try to apply for a government grant and see if I can set up a manufacturing plant and just start building them. And once they see the finished prototype, how it works, producing clean, free electricity, maybe by then somebody will be interested in taking a look at it. Okay, that's it for this for now. I'll talk to you later. Thanks.